All right, I guess we can get started. Welcome back. Nobody here for the first time? All right, great. Let's talk about the u-substitution. That's what I said a few words about last time. We're going to do it for real this time. The u-substitution. This is the, I suppose, the most basic of the integration tricks that we're going to talk about this semester, and the only one that I assume that you've all seen this before, although, I mean, I'm about to explain it, so it's okay if you haven't. The u-substitution, there are a few different ways that people learn to write it out, and so if you are used to doing it slightly differently than how I do it, then that's totally fine. You can do it however you like, but I'm usually going to do it, the way I do it. But the idea, I will write out sort of in words, the basic idea here. It's for integrals, first of all. You don't do this with derivatives. And it's usually when we have stuff inside other stuff. That's the typical situation when you use the u-substitution, when you have things that are stuck inside of other things. And the strategy is you find the inside part and you make that u. And then you find the du. There's always a u and a du. You find the inside of something or other, and you make that the u. And this, what makes the u-substitution kind of difficult is that this step is sort of up to you to decide for yourself what you want the u to be. And when there's an inside and an outside, you usually want to choose the u to be the inside part, but there's some examples where you have to choose the u to be a somewhat weird thing to make it work out, and there's a bit of finesse to it. You have to do a bunch of examples to kind of get used to it. But anyway, this is the usual situation is you choose the u to be the thing which is on the inside of something else. And then you take the derivative of u, and this is called du. And then you rewrite everything in the integral. Usually, the integral starts off as being some stuff involving some other variable x. You rewrite everything inside the integral. Rewrite everything in terms of u instead of in terms of x. And then you do the integral in terms of u. So you do the integral, that is to say, like the antiderivative in terms of u. And at this point, you're basically done. You've done the integral. And then at the very end, there's a step which is always easy, and that is just to replace the original variable, like whatever you started with, which you turned into u's. Then you put it back in the original variable at the end. This last step is always easy to do. Sometimes you forget to do it, but replace the original variable. This is the idea or the procedure of doing the u-substitution. Let's just do a simple one, and then we'll get to some fancier ones in a moment. How about 2x times x squared plus 10 to the power 6 dx? All right. So first step is to, I suppose there's like a step 0, which I didn't even write here, and that is you have to look at this and realize that you need the u-substitution. So you can't do this one without the u-substitution. The reason you can't just, you might just say, oh, can't I just like this x do the integral by just like this x becomes 1/2 x squared and this x squared becomes 1/3 x cubed? The answer is no, because there's like all this other stuff all around it. So one problem is there's a multiplication right here, 2x times this business. Inside of an integral, if you see multiplication, you cannot just do the integral of each of the two parts separately. All right, so that multiplication is bad news, and then also for the same reason, this 6th power sort of screws everything up. You can't just do the integral inside of a 6th power like that. So you look at this, you realize, okay, I'm going to have to do something special. I'll do the u-substitution. We choose the u to be the inside of something. In this case, I'm going to choose x squared plus 10 because it's inside of the 6th power. What about the 2x over there? I don't know, really. Hopefully that will take care of itself later on. If you know how to do this, you will see immediately what takes care of the 2x. But anyway, I chose the u to be the inside of something. Next step that I wrote up there, take the derivative of u And this is what I call du. So the du in this case, finding the u is just a choice. Like I kind of made that up just by looking at this. But once you choose the u, everything else goes, you are calculating now. Du is the derivative of u. Someone want to say? What do you get? 2x. Yes, and some of you said dx. All good boys and girls include the dx as part of the du. This is just something that you should do. If you forget to write dx there, it'll probably be okay, although there are some situations when you'll end up confusing yourself. So technically speaking, if you want to do it right, the du always includes the dx. All right? You might work out okay if you forget to write it there, but technically you ought to write it. All right, and now, so I have done what you see, the steps up there. Take the derivative of u, that's the du. All right, next, rewrite everything in terms of u. Maybe I'll say instead, just more specifically, u's and du's, right? You also want to use du. So I look at this here and I just try using this, u is x squared plus 10 and du is 2x dx. I try to replace as much as I can with the goal of eliminating all the x's entirely and writing everything just using u's. So the first thing, if you know what you're doing, you can do this all at once, but I'll write out a couple steps here. The first thing I'm going to do is just put the u right where it is. So u is x squared plus 10. So right there, this thing becomes u to the power 6. And I'll just leave the rest like it is for now. Although, like I said, if you know what you're doing, you can probably skip these intermediate steps. U to the power 6. And then, so I consider this, u to the power 6 is kind of like all taken care of because my goal at this point is to write everything in terms of u's. What's left over is 2x and dx. And what am I supposed to do with 2x and dx? Lucky for us all, 2x times dx is equal to du. So I'm going to, if you like, I'll just write one more intermediate step. Put these guys together, which is legal because it's all multiplication there, so you can write them in whatever order you like. And now 2x dx is du. So this becomes u to the power 6 du. All right? And now the substitution step is complete. Rewriting everything in terms of u's and du's. How am I doing so far? Any questions? All right. Next step, do the antiderivative in terms of u. The idea, like if you're doing this correctly, or the whole purpose of the u substitution is you start with something that looks quite complicated, but after the substitution looks really simple. And so now I can do the antiderivative. This is just 6 power, so I'm going to get 1/7 u to the 7. U to the 7 plus c. And you'll notice at all along I've been writing the integral sign. I hope that you have also been writing the integral sign until this point. I know there's some like integral sign haters out there. They like just don't like to write it. And I'm like, hey, why didn't you write the integral sign? And they're like, I can remember there's supposed to be an integral sign. Okay, you do you, but you should, I mean, it's technically not correct if you don't write the integral sign, but you ought to write the integral sign. It's kind of like, you know when you meet those people who like they write emails but they don't use vowels? You're like, bro, why don't you use vowels? And they're like, I don't need to do that. I remember, like I can still tell what it's supposed to say. And I'm like, well, yeah, I guess I can kind of tell what it's supposed to say, but it's weird. Just write the integral sign. Anyway, why didn't I write it here? It's because that is the step in which I actually did the integral, and so you shouldn't write the integral sign anymore because I just did the integral. All right, final step, replace the original variable. This is more or less like a technicality. I mean, this is kind of the answer. It's just that the original problem was stated in terms of x, and so you ought to write your answer in terms of x also. So this is always an easy step. It's just u equals this, so I'm just going to put that in where the u is. So my final answer then is 1/7 x squared plus 10 to the 7 plus c, like that. The end. All right. Anybody got thoughts about that? This is, I would say this was an easy one. It can get a little bit harder than this, and it can also get more than a little bit harder than this, but this is like an ordinary one. All right. All right, let's try. I got just a couple more examples, and then I have some for you all to try. In a typical example, you have to do an extra little step. We kind of got lucky here in that after I plugged the u in, the rest of it, everything that was left over, sort of magically equaled the du exactly. And that actually doesn't always happen. So here's an example where sometimes we need to, I will call this, divide a constant. And this is, when we do this extra little trick, it's not really a big deal, but this is one that sometimes people write in different ways. It's fine. How about that? X squared, square root of 1 minus x cubed. Anybody like to suggest what should I choose to be the u? What do you think?
1 minus x cubed.
1 minus x cubed. Yeah, why did you pick that?
Because it's inside of the square root.
Because it's on the inside of something or other. Yeah, it's inside the square root in this case. Really, you have two choices to pick, the x squared or the 1 minus x cubed. And you should choose the 1 minus x cubed because it's on the inside of something. All right, then the du, I just take the derivative of that. I get negative 3x squared dx. All right? And now if you know what you're doing, you should already be sort of looking ahead at this point to say, do I see negative 3x squared dx over here? And the answer is kinda. I see x squared and dx. I actually don't see negative 3 anywhere over here, but this is where this extra little step here, divide a constant, come in. Because I don't see negative 3 anywhere, what I'm going to do is this du here, I'm going to take this negative 3 and divide it to the other side of this little equation. It will say negative 1/3 du equals x squared dx. And now this does match exactly because what I see over here is x squared and dx, and that's what I see right here also. All right. Some people, when you write this, some people would prefer to write here instead of dividing in this spot. You multiply by 1/3 and also by 3, and then do something. It ends up being the same, and if you prefer to do it that way, that's totally fine. Anyway, let's try to plug everything in. So I'm going to replace all these x's by u's. First, I'll do this in a few steps like I did last time. First, I will just put the u where it is. It says x squared, the square root of u dx. And now if I like how that u looks. The parts which I have not yet substituted are the x squared and the dx. So if I write it this way, I just rearrange the ordering a little bit. And I forgot the square. And now what do I do with x squared dx? X squared dx equals negative 1/3 du. So this becomes integral square root u times negative 1/3 du. All right. And now the substitution is complete. That is, there are no x's anymore. It's all u's. And so the next step would be to do the integral. Although sometimes you can do, I would actually suggest one little simplification before I do the integral. Anybody got a feeling?
Bring the negative 1/3 out.
Yeah, I'm going to factor this constant multiple can always come out of an integral. That will just make things a little easier before you try to do the integral. Negative 1/3 integral square root u du. All right? And now we're going to take the integral. How do I handle square root of u? Yeah, that's the same as u to the power 1/2. So this one last step to write here, like this. And now I'm ready to do the integral. As usual, I'm writing out like every possible little step here. If you know what you're doing, you can skip a lot of these intermediate steps. The integral. Negative 1/3 stays there, and then on the inside, I'm going to do the integral. We increase the power by 1, so 1/2 becomes 3/2, and then I divide by 3/2 in the front. I'll write it as 1/3/2, or you could write 2/3 there, which is the reciprocal of 3/2, u to the 3/2. And then the very last step, as always, replace x where the u is. So my final answer is negative 1/3. Maybe I'll write 2/3 here. And then instead of u, I put 1 minus x cubed to the 3/2. There you go. All right. Any thoughts about this one? This one was also fairly routine, although we had to do that extra little divide the constant step. I hope that it looks familiar to everybody. One thing about the u-substitution, which is a good idea if you have a couple extra minutes on a quiz or something, you can always check your answer. Anybody know how would I check my answer if I wanted to? Yeah? Yeah, take the derivative of the answer, and if everything is correct, you should get what I started with. So can we just try that? This, if I take the, maybe I'm going to try and check it. If I take the derivative of the answer, I have this constant out front, which I guess is -2/9. But then taking the derivative of this part, I'm going to have to do the chain rule. So I bring the exponent down here. That's the derivative on the outside. It becomes 3/2, and then the same thing on the inside. And then I decrease the power by 1, which makes it 1/2. And then by the chain rule again, I have to multiply times the derivative of the inside, which would be -3x². And then the derivative of the plus c is 0 because that's a constant. And then does this actually equal what I started with? It really does. All of these things can cancel. The 2 cancels. This minus sign cancels that minus sign. Here I have a 9 in the denominator, but I have 2 3s in numerator, so those will also cancel. And anyway, the whole thing is just going to equal x² times that, which is indeed what we started with. So I like that. All right. You can always check your answer after doing the integral by taking the derivative of what you got. And it ought to match what you started with at the very beginning inside of the integral of this thing. Right? Great. Let's do one more of the sort of ordinary type, and then I have one sort of harder one, I suppose. How about, and I got some for you all to try. Sine x over cosine to the 4x dx. This one's a little weird because there's nothing here that obviously looks like the inside of something, although there is kind of something inside of something. Anybody got an idea here? Yeah?
You said u is cosine?
Cosine, yeah, this is a good idea. I think the realization, well, first of all, you should think to yourself, what does this cosine to the 4 even mean? This is a weird thing, and actually I'm kind of a hater of this way of writing things, although it is the normal way, and I'm going to write things this way. But cosine to the 4x means this, cosine of x to the 4. And when you write it that way, it now does look like there is something on the inside of something. It's that cosine of x. And this is what he said. We should choose u to be cosine of x. All right. And then what's the du?
Sine x dx.
Negative sine x dx. Great. All right, and let's try and plug them in. So I put the u where it goes, first of all. Come on now. Sine x over u to the 4, and then dx. And now we need to do something with sine x and dx, but lucky for us, that basically equals this. It's not exactly this because of the negative here, but I can do the old, just put the negative on the other side by dividing it over there as if it was a constant. It is a constant. Negative du equals sine x times dx. All right, and this is a slightly, I guess, slightly weird substitution. I'm going to pull this sine x dx apart from the fraction here. So I'm going to write this instead like that. And then it will be very clear. Those are the same, right? You can sort of rip something out of the numerator of a fraction because that's the way that multiplying fractions work. If you're going to multiply this, it would go into the numerator. All right, and then sine x dx is negative du. So this is integral 1 over u to the 4 times negative du. I'm going to factor that minus sign out. And now I'm feeling good about this. 1 over u to the 4, sorry, du, I wrote dx. Right? Everybody with it, I hope. And how do we handle this for the antiderivative, 1 over u to the 4?
U to the negative 4.
Yeah, you write this as u to the minus 4 because it's in the denominator, and then do the antiderivative. We increase the power by 1. The power is negative 4. It will increase and become negative 3. and then you divide by -3 in the front. So it's going to be, I had a minus sign to begin with, and then 1 over -3, u to the -3. And I suppose we can cancel those minus signs, but this is 1/3 u to the -3, all right? And then, as always, the last step is to replace the original variable, which is cosine x. So my final answer will be 1/3 cosine x to the -3 plus c. All right, you could write cosine -3 of x if you want. I'm not into that, but that is how people write it. All right, excellent. Great. These are what I would say, I would describe these as kind of like ordinary examples of the u-substitution, where you sort of, I hope that these all seem familiar to you. I got a couple for you to try, but actually I wanted to do one more thing first. Two more things first. One is a simple thing. We ought to do one example like this at least. What about a definite integral with the numbers? This again is something that people like to do. People like to do this in two different ways. I'm going to do it my way. You can do it your way if you want to. The basic idea here is you just do all the same stuff, the u-substitution, and then wait until the very end to plug in the numbers 1 and 4. All right, so I'm going to, maybe I'll do this one a little more quickly. What do you want to choose the u in this case? 3x squared plus 5, I hear him say. Great, and then the du is a derivative of that, 6x dx. And then just because I know what's up, I'm going to divide the 6 over to the other side there and say 1/6 du equals x dx. All right, plug in my business here. It becomes integral x u to the 10 dx. This is integral, if you prefer, u to the 10 times x dx, and then x dx is 1/6 du. So this is u to the 10 times 1/6 du. You'll notice I've stopped writing the numbers here. While I'm doing the substitution, I'm not going to write the numbers. That's because you have to keep it straight. The numbers refer to values of x. They do not refer to values of u. So one way that some people like to do this is you change the numbers to the corresponding values of u in the middle here. That's fine. I'm going to do it in a different way. I'm going to just leave the numbers for now, do the whole answer in terms of x, and then plug the numbers in for x. It's the same method. I mean, you'll get the same answer either way. That's how I like to do it. Anyway, bring the 1/6 out, and then I'm going to do the integral. So this is 1/6 integral u to the 10 du. Do the integral. It's 1/6 times 1 over 11 u to the 11. Ordinarily, you put the plus c, but because I intend to plug the numbers in, I'm not going to put the plus c. And then finally, replace the x. I can multiply 6 times 11. I remember my 11s. 3x squared plus 5 to the 11. All right. And now I'm going to put the bar and the 1 and the 4 and plug the 1 and the 4 in. All right. Like I said before, you may have learned it differently, where you change the x values into u values in the middle, and then you would plug in at this point rather than, I'm kind of doing extra steps here because I didn't do them earlier. You can do it either way around. Anyway, my answer will be 1 over 66, 3 times 4 squared plus 5 to the 11, minus 1 over 66. Same thing, but I plug in a 1. 3 times 1 squared plus 5 to the 11. That's it.
We don't need to plug in there.
Certainly not.
All right.
Surely not. Yeah, you should not try to simplify any of this. All right. Great. Okay, this is just how to handle plugging the numbers in. No big deal. Okay, one last thing, which is, I suppose, kind of a big deal. Sometimes you need to do some extra fancy tricks. Sometimes you need to get tricky. Here's an example. How about that? X times square root x plus 1. You got an idea? No. Stretching. Yeah?
You set u as x plus 1 and then isolate x and then plug that in?
Mm-hmm. Yeah, so this is an extra level of tricks with the u substitution. You set u equals x plus 1. This is, that's a natural choice because that's on the inside of the square root. All right. So I go u equals x plus 1. Okay, what's the du then?
dx.
Yeah, du is just like 1 dx. All right. This is not wrong. Although if you don't know what's up here, you might kind of get stuck at this point, because if I now try to plug stuff in over there, as I usually do, I'll just put the u in first. It becomes x root u, and then I guess du is the same as dx, so I can just change dx to du. But the question is, what am I going to do with this extra x here? Like usually in the previous examples we've done, this extra x would have also been part of the du, but it's not in this case. And we see what to do? He actually said it a moment ago, yeah? Yeah, so you can see the x up here now. This is weird, but in some examples, you've got to do this weird thing. I am going to subtract the 1 there to like solve for x here. X equals u minus 1. So sometimes you need to solve for x in terms of u. This is usually not necessary, but there are some sort of weird examples where you have to do this extra step. So down here, x times root u, x is u minus 1. U minus 1 root u du. All right, you better put those parentheses. I know there's parentheses haters out there. If you don't put the parentheses, it means something different. So put the parentheses. I'm kind of a stickler about the parentheses. All right. Okay, now what? Actually, it's not clear that this, it's not wrong. I didn't write anything incorrect, but actually, even at this point, it's not clear that this is actually going anywhere. Remember, the whole point of doing the u substitution is you start with something complicated and it becomes something simple. But actually, that didn't really happen here. I mean, it was complicated here, and I don't know, to me, this looks kind of the same. Like, it's not the same, but it's not much simpler. Any ideas? Actually, it is a little bit simpler, yeah? Yeah. At this point, you can write root u to, you can write root u as u to the 1/2 and then distribute it across here. And that's the advantage. It's because here you're not allowed to distribute inside of the square root. Everybody knows that. But here, it's like the other thing is in the square root, and now you actually can distribute. So it is integral, okay, u minus 1. First I'm going to write u to the 1/2, like that. And then I'm going to distribute like so. And when we distribute, we add exponents. So that u I think of as u to the 1. And then when I do that distributing, it becomes 1 plus 1/2 up there, u to the 3/2. And then minus u to the 1/2. And now that is an integral that we can do just by doing the powers each time. So the first one, the 3/2, it increases and becomes 5/2. So it's going to be 2/5 u to the 5/2. Because I divide 5/2 in the front, which is the same as multiplying 2/5. And then minus, this one is going to become u to the 3/2 with a 2/3 in front. Like that. All right, and then the very last step, as always, I replace the original variable. So instead of u, I'm going to write x plus 1 each time. So my final answer is 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2. There you go. All right, this is an extra little trick. It's not that hard to do, but it's a little weird, and especially if you haven't seen this before. And I'm not sure if everybody learns about this weird trick in high school, but it's not so hard. You just got to know how to do it. Any questions about that one? All right, I got some for you all to try. Right here, right here. try these. How about this one here? Integral from 0 to the square root of pi of x sine of x squared dx. I got this one here. And this here. All right, see what you think. Feel free to chat with your friends, your new friends. Yeah. It's a good idea. I don't think it works. And it's very good. I'm not, I assume it was, but yeah, like, it's weird. Yeah. Have the U part, the DB part. If you make this the DB part, then but if you make this the U part, it's not big. Yeah, this it's not that good? All right, here. How's it going? So far, 4. Okay.
Oh my gosh.
You can do that.
I just realized that. I'll just leave it with that, and then I'll just
get rid of it.
Yeah, that's what I'm saying. Oops.
It's looking good. Is that okay here?
Yeah, that looks really
Yeah. Good start. All right.
It's because I'm so used to Oh, yeah. Oh, got it. They have this?
Oh, yeah, it's like right there. Yeah.
Yeah. It's not wrong, but you should. I would say this part of DS. So you know this solution. You want one exit. And then just leave it. Well, that means it's a square. And that you can get. All right. This is good so far.
Cosine of zero is just one.
Yeah, okay.
So she can't still do an hour.
No, it wouldn't cancel out, it would just be right.
We're gonna go with it. I'm going with it.
Yeah. Great. Yeah. Everyone okay?
Okay.
Good here?
What? Oh, which one? This? So, you go, you do the like regular DU stuff, and then you get here. So, you can cancel one of these x's out, because that next DU divided by 2 is that.
Yes.
So you
I
can
forgot.
divide by 2
we get
DU,
this.
and you take out an x dx. So
Yeah, you have to do one of these sort of weird
dx, take
things
out
like the
that,
last
so that
one
becomes
that I
an x
did.
squared, you do the 10/2 du, and then you solve for x squared, because now you just have x squared, which is u minus 1.
So
You plug
with the
in
dx,
x
you
1
want
and
one,
distribute
you want one x.
this,
You have dx and x.
and then
So
you get
just one x.
u to the 11th over 2 and u to the 10th over 2.
And then that x.
Or minus u to the 10th over 2, and then u.
Negative half cosine.
Doing all right?
Yeah.
Sorry, I never came by. Good? Yeah, this one is part of the memory trick. It's so weird.
Yeah, I
Yeah, this is differential. I would say, you wanted you to get something which is inside, so you should. Doing okay? It looks good.
This one?
Yep. Or are you stuck on this one?
Yeah.
Oh, yeah, this is the hard one.
Oh, okay.
This is good. You can actually calculate these cosines. Maybe you like cosine of 0, and then root pi squared is just pi.
Okay.
So you can do Let's take a couple more minutes and then we'll go over them. I know not everybody's
Because my teacher inflated all of our grades because she wanted us to get into all the college schools. I failed to realize that they were getting placed high for math. But yeah, probably deserved like a C. But I have like an A plus.
All good here?
Yeah, so you're good for this now.
I don't know.
Yeah, this is literally the same class I took last year.
And
I get dx in terms of du. So then I replace it on du dx. And then the x's can cancel out. So the x's here cancel out. So 2 in the denominator, which just becomes 1/2, and I brought that out. So then you're just left with sine u, because these two x's cancel out, sine u. So then you would just solve it like normal sine.
But you use the right exponent, use the right u, it's super easy.
Sine is negative cosine.
Sometimes it's just trying to decide what you use.
Then you will then do like the integral part, and we just that 1/2 would just go just cosine.
So now this
Oh, well, that's what sorry. Thank you.
now at this point.
You guys on Fizz, you see the snaps just chats from yesterday? Dude, the one.
You can always remember a concept.
Somebody just keep scrolling through
All right, can we talk about these? I know not everybody's done, but we've only got about 10 minutes left. So the first one here is fairly routine. I mean, this is like a pretty ordinary one. U equals x squared. The du is 2x dx. And then I divide the 2. 1/2 du is x times dx. And what I see over here, this is going to be sine of u. And then what remains is x and dx, which is 1/2 du. So after, I'm going to do this one kind of quick just because this is sort of the easy one. It'll be sine of u times 1/2 du, right? Sine of x squared becomes sine of u, and then the other stuff is x times dx, and that's 1/2 du. All right, and then I'm going to move the 1/2 out of the integral, because you can do that with any constant multiple, and then do the integral. I get negative 1/2 cosine u, and then I'm going to plug the x back in, negative 1/2 cosine of root x. And I have to plug in, not root x, x squared. And I have to plug in 0 and root pi, like that. Doing all right? And then we just plug them in. So this is negative 1/2 cosine of root pi squared is just pi. And then minus negative 1/2 cosine of 0. And then you can actually do these. Cosine of pi is -1. Cosine of 0 is 1. So this becomes negative 1/2 times -1. Minus, that's a minus and a minus, so I'll make it a plus. 1/2 times 1. That is, those are both plus 1/2, and they add up to 1. All right? That's what I got. 1. Any thoughts about that one? There's some opportunity to just mess up the numbers in there, but as I was walking around, it looked like most people were doing great. All right. Okay, how about the next one? This one is a little more complicated, although still similar to one of the ones that I did. We are going to choose, well, what did you choose for the u? 1 cubed. Great. And then the du is negative 3x squared dx. That's just the derivative. And then, just because I know what's up, I'm going to divide the negative 3 to the other side. So negative 1/3 du is x squared dx. All right? And now we plug them in. This becomes integral x squared over u to the 4 dx. You can sort of separate out the fraction, that is to say, like pull the numerator out of the fraction, or if you prefer, some people would rather just use a negative exponent at this point for the u. So this is the same actually as integral u to the -4 x squared dx, right? I'm just writing this instead of like a fraction, writing it like multiplying by the denominator, which is a negative exponent, right? And then x squared dx is negative 1/3 du, so this is now the end of my substitution, negative 1/3 du. And then this, as always, you can move the constant outside the integral. So minus 1/3 integral u to the -4 du, like so. That's a 4. Sorry, sometimes my u's look like 4s. It's all right. I am a work in progress. All right, And then all of our substitution has happened, and so now we can just do the antiderivative. It's minus 1/3. The exponent will increase to -3, and then I divide by -3 in the front, so it's actually another minus 1/3 u to the minus 3 plus c. And this all ends up being 1/9. I put the x's back in, 1 minus x cubed to the minus 3. Does that look all right? I hope that's what, as I was going around, that seemed to be what most people are getting. Most people were getting that. All right, great. Let's do this one. This one is the hard one. It involves a weird trick similar to the weird trick that I did at the end, although this is even ever so slightly weirder than the one that I did. Anyway, you should begin by choosing u to be the thing on the inside, as we usually do. X squared plus 1. Then the du is 2x dx. And now you realize that you're going to have to do something weird. Let's try to plug in like as much as possible. I would write x cubed and then u to the 10 dx. Maybe I'll sort of put these guys together. U to the 10 I'm satisfied with. I'm not sure what to do with x cubed dx. All right? Why am I not sure about x cubed dx? Well, x cubed dx is not equal to that, and not even if I divide the 2. I might as well divide the 2. But that doesn't really solve my problems. This is not x cubed, it's just x here. And also, that you would maybe consider solving for x up here, but that's also not going to be helpful here, because this is a cube, but that's a squared. What did you end up with? I saw some people figure this out. What do you say?
I divided instead of keeping the x with the dx, I moved it to the du so that I could cancel out one of the x, so it becomes x squared.
Right.
And then I did the trick to solve for x in terms of u,
Mm-hmm.
and then I got the square root of u minus 1.
Yeah,
and
great.
I plugged it in, so then I was left with u minus 1 because I was able to cancel out the square root.
Mm-hmm. Yeah, so there's a lot of steps that she just said, but the first important step is to realize that I actually like when one of the x's goes together with the dx. Here I have sort of like 3 x's here. One of them I'm going to put together with the dx. So I'm going to think of this. This is probably a step you would only think about in your head, but I think of it like that. Put one of the x's with the dx, and then this x dx I can write in terms of du. So I'm going to write that one. This is u to the 10. I have a stray x squared. I don't know what I'm going to do with that, but x times dx is 1/2 du, like so. All right? And now what am I going to do with the x squared? I do the other trick, which is solve for x in terms of u. And actually, you don't really have to solve for x here. You can just solve for x squared. So this right here, you can say x squared is u minus 1. And then that's what I'm going to put where I see x squared. I'm going to put u minus 1. If you could solve for x entirely by taking a square root, which you would then square again, and it'll go away. So that's a little tricky, but anyway, it looks like this. Right? And now these are all in terms of u's, and we can distribute the x to the 10 across this one over here. So let's take the 1/2 all the way out of the integral. Distribute u to the 10. I get u to the 11 minus u to the 10 du. And now we just do this integral. They're just added together, so we do them separately. 1/2 out front. 1/12 u to the 12 minus 1/11 u to the 11. And then we put x back in for the final step. So our original substitution was u equals x squared plus 1. So this is a little complicated. X squared plus 1 to the 12 minus 1/11, x squared plus 1 to the 11. There you go. Any thoughts about that one? This was the hard one. I hope you got something like that. All right, I think that'll do it for today. That's about all of our time.